good, I don't know what to say. Okay, good afternoon. So at least it's my afternoon. I'm Marco Maratea. I'm chairing this session, and so there is Gerardo who is co-chairing this session. This session, I'm Marco. Okay, this session is about ASP and logic programming. It is the first session out of 3 about this topic. Okay, this session is made on 2 presentations, and so just I remember to the audience that we will have presentation will last for around 20 minutes. So this means that 15 to 17 minutes of presentation plus 3 to 5 minutes of question from the audience. Okay, and we have 2 papers, and now we can start with the first one. Maybe when there is some time left, I will remind the speaker, okay, with my hands signing the minutes that they have until the end. But anyway, let's start with the first presentation. The first presentation is by Panos Rondogiannis and Ioanna Symeonidou. And the paper is titled Stratified Disjunctive Logic Programs and the Infinite Valued Semantics, and Ioanna is presenting.
Hello from Athens, Greece. Let me go ahead and share my screen. All right. So again, the paper is joint work with Panos Rondogiannis, and it's titled Stratified Disjunctive Logic Programs and the Infinite Valued Semantics. Let me go ahead. So we're going to be talking about disjunctive logic programming, which is an extension of classical logic programming, where we can have disjunctions in the head of clauses. For example, in this little program, we are told that A or B holds if C holds, but we can never really know if A should be true or false. This program has 3 models that capture 3 possible scenarios, and the first 2 models are both minimal. Obviously, we cannot choose one over the other. So, unlike the case of traditional logic programming, where we have a unique minimal model, things here are already more complicated. Now, traditional non-disjunctive logic programs are classified based on the use of negation. And at the core, we have positive programs without negation. Then we have a class of programs that make a sensible, so to speak, use of negation. I will remind you of this concept later. And then we have the superclass that includes all programs with or without negation. The meaning of positive programs is captured by the minimum model semantics. And the meaning of stratified programs is captured by the perfect model semantics. And for the general case, we have a choice between the set of stable models and the well-founded model. Obviously, each of the semantics extends the ones below it. And this is how the classes are extended in the direction of disjunctive programming. Let's see how the semantics are extended. So as I showed in the example, one minimum model is not enough for positive programs. We have a set of minimal models. And obviously, it shouldn't be enough in the case of programs with negation. So we have a set of perfect models to capture the meaning of stratified programs. In the case of the stable model semantics, we already had a set of models, so no surprises there. We have a set of stable models again. But then we get to the well-founded model semantics, and suddenly things get complicated. In our paper, we'll look at 9 different disjunctive versions of the well-founded semantics, and there are even more. Most of them are different from each other, and none has been crowned best, or at least most popular. And there is another problem here. Out of the 9 semantics, 5 do not extend the perfect model semantics as we would expect. Actually, only one is proven to extend it, and we have no results for the other three. This makes one think that maybe the problem lies with the perfect model semantics, and some authors actually have suggested that this extension is where we went wrong and not this one. So now, not only do we have more well-founded semantics than we can handle, we're also second-guessing the semantics of stratified programs. I don't claim to have a definitive answer to either of these problems, but what we're going to do in this presentation is we will focus on one of the 9 semantics that I mentioned, the infinite valued semantics, and we're gonna discuss how it might be a good place to start. So first, we will have a quick look at the different approaches and how they compare to each other. We will see that the equivalence results between 2 semantics are very rare, and various examples show that they are mostly different. Then we will show that the infinite valued semantics has some nice properties in the class of disjunctive stratified programs. Indeed, it seems to be very good at capturing the meaning of such programs. And we feel that this is important for any semantics that wants to be named the ultimate disjunctive well-founded semantics. At the same time, in every example we will look at, it behaves exactly like the perfect model semantics. So let's start with the comparison results. These are the 9 disjunctive semantics we have researched. The oldest approach is from 1989, while the last one is from 2007, and it's the infinite valued semantics. It's interesting that some authors, like Panos or Gabriele and Pierce, have contributed to more than one different proposals. And this is an overview of the comparison results which we have found in the literature or inferred from the literature. In some cases, you will see that 2 semantics are different from each other. In some cases, we see that a semantics may be stronger than another, which means that it can infer more information from a program. In other cases, we will find that the semantics is incomparable to another, neither stronger nor weaker. And there are only 2 equivalence results. In particular, the perfect model semantics is, the stationary semantics extends the perfect model semantics, and the static semantics, which is generally stronger than the D-WFS, can be equivalent to it under some restrictions. Now let's have a look at how the infinite valued semantics works. In this program, both P and S, they should be true. However, one could say that P is somehow truer than S because there is a clause that says that P should be true, while S is only true because Q doesn't have to be. Now we want to add a new truth value, say T1, for this true by default predicate. And we consider this new truth value to be weaker than the real true value T0. For symmetry, we also have a weaker false value compared to the real false value F0. So now negation as failure can be seen as a combination of ordinary negation with a weakening. And as negations can be iterated, our truth domain needs a sequence of weaker and weaker and weaker truth values below the real true and above the undefined value, and a mirror sequence of weaker and weaker false values above F0, the real false, and undefined. So every non-disjunctive program is proven to have a unique minimum infinite valued model, and if we collapse all true values to the classical true and all false values to the classical false value, or in other words, if we just drop the subscripts of truth values, then we get the well-founded model of the program. Now, let me also take a minute to remind you about stratification. A stratified program is a program where we can partition the symbols of the program into disjoint sets called strata, so that every symbol in the body of the clause is placed at the same or at a lower stratum than the symbol in the head. Negated symbols in particular must be placed in a strictly lower stratum. And for disjunctive programs, we also have one additional restriction, that the symbols in the head of the clause must all be in the same stratum. What this means is that a stratified program, in the stratified program, there can be no circular dependencies that run through negation. And this allows us to define a priority ordering for the symbols of the program, so that we can evaluate a symbol after we have already evaluated all of its negative dependencies. And for this reason, stratified programs have a clear meaning and nice semantic properties. And so let's see how the infinite valued semantics works for this class of programs. Now, I will show you how I will show you how a set of consecutive strata defines a self-contained subset of the stratified program. And it's probably intuitive, but it's not trivial, that every minimal infinite valued model of the program is also a minimal model of every such subset. Let's look at an example. This program here has only one stratification, with S0 being the lowest stratum and S2 being the highest. If we take the first two strata and the clauses that whose heads are in these two strata, then the bodies are also in the same two strata. In this sense, this is a self-contained subset of the program. We can actually evaluate every symbol in this subset without having to look at the remaining clauses or in the third stratum. So this is what we're talking about when we talk about strata defining subsets of the program. These are the two minimal models of the program, and they are both minimal models for this subset. Another interesting property is that if we collapse a minimal infinite valued model of a stratified program into a classical three-valued model, then it will still be minimal. Let's look at the same example from the previous slide. In the first minimal model, P and Q have the true values. So this is the collapsed model. And in the second minimal model, P and R are the ones that are true. So this is the collapse of the second minimal model. These two models are not only minimal, but they are also the perfect models of the program. And the perfect models are also always minimal. Then now let's get to the main result of the paper. The theorem shows a relationship between the number of strata and the values assigned by a minimal infinite valued model. Actually, this relationship is shown by induction to hold for every stratum of the program. Let's see, notice that this sets a bound for the number of different values, which is a noteworthy improvement over a previously known bound for the general case, and that a similar result was not known for non-disjunctive stratified programs. It is also very important that the undefined truth value is not contained in the set of possible values, which is also a well-known characteristic of the perfect model semantics. Now let's look at our example. Indeed, the symbols in stratum S0, Q, and R are given values T0 and F0 in both cases, in both models. And the symbol in S1P is given values T0 and T1, while the symbol in S2 is given values F1 and F2. Of course, no symbol is left undefined. So with these three properties, we show the proximity of the core ideas behind stratification and the infinite valued semantics. And we showed that the minimal infinite valued models of stratified programs have a tiered structure that corresponds to that of the stratified program. We also feel that the semantics seems to have some connections to the perfect model semantics. And it would be interesting to prove the equivalence of the two semantics or some other relationship between them. It would also be interesting to have more definitive results regarding its relationship to the two other disjunctive well-founded semantics. An immediate consequence operator would be a valuable tool for the first two problems. We don't have one for the disjunctive case at the moment. We were also wondering if we could improve the bound of truth values known for non-stratified programs. At the moment, it is set to the number of different symbols appearing in the program. But of course, the real question is, could we someday agree on the infinite valued semantics or some other semantics as the widely accepted disjunctive well-founded semantics? Well, it seems that first we need to agree on how to read certain programs like this one. This is one of the most widely discussed programs in the literature, and in a way it divides the semantics into two categories. The ones that say R should be true, and the ones that say that it should be left undefined. The program is stratified, so having symbols left undefined is against our intuition. And if we read the program from the viewpoint of, say, a judge who is trialing someone for having two wives, then we are probably correct. The judge should declare the defendant innocent, because from this program we cannot infer that he is married to the one woman or the other, even though we do know that he is married to at least one of them. The perfect model semantics, the infinite valued semantics, and some other semantics do agree with this reading of the program and make R, or declare innocent, true. But some other semantics, they read the program in a different way. If, for example, we know that a professor is a good scientist, and he is a good teacher, or maybe both, then can we ever decide to fire that professor? Probably not, until we can actually prove that he doesn't have one of these qualities. So maybe leaving R undefined is the right way to go in some cases. And this is one example of all the gray areas in disjunctive programming, which explains why we have, and maybe even why we need, so many semantics. So this is all for me.
I don't see any other question on the chat. Okay, so we can thank Ioanna again.
Thank you.
And so we can move to the second talk, second and last talk of this session, which is by André Thevapalan and Gabriele Kern-Isberner, and the title is Towards Interactive Conflict Resolution in ASP Programs, and André is presenting.
Welcome to my talk on the subject towards interactive conflict resolution in ASP programs. So we all know there's fast progress in medical research, and especially in cancer research. And in a previous work, we implemented a decision support system together with a hospital to assist medical experts to find individual cancer therapies for patients. And its core is an answer set program, and there we have one main issue we have to focus on is the update of the knowledge. And yeah, as we know, inconsistency is easily possible when updating and revising knowledge. And for logic programs, there are already many theoretical approaches available, but we wanted to focus on an application which is usable in the real life, which is maintainable and guarantees us an update which is consistent and correct. And with correct, we mean that a medical expert would say that the knowledge is correct. So our approach has two main steps. First, the detection of conflicts, and then the resolution of conflicts. And in our opinion, it's important if we want to have correctness that we include the medical expert. And in our approach, we our method will do most things very in an automated way, but at the end, the medical expert has to decide which rules to modify. And that is why we say the medical expert has to be included in the resolution process. So just a quick overview regarding the notation I will use. So in our answer programs, we have the literals L. For the classical negation, I will use a bar, and for the default negation, I will use the keyword not. And our rules are non-disjunctive, so we have only one head literal and a body, which can be many literals, default and classical negated literals. And because of the default negation, many multiple answer sets are possible. So just a small example here, rule 3 and 4 are applicable, but only one of them each time. So we have two answer sets. Okay, so let's look at a small scenario where we have a program P1, which shall represent clinical guidelines. And in our case, let's say we have a patient with a metastasized triple negative breast cancer, which is often abbreviated with TNBC. And the patient wants to get treated at the clinic. And it is generally known that the treatment of TNBC has a low success rate. And then let's assume that studies find out years later, in this case, 2 years ago, that adding a new therapy type, in this case, immunotherapy, to the therapy regimen can increase the success rate if the patient is not in a visual crisis, which means if the patient has not severe organ failure. And now we want to update P1, our initial knowledge, with P2. And here we can already see that R3 and R5 can cause inconsistency because they have complementary head literals. And if the body of rule 5 holds, if it is true, then the body of rule 3 is also true. And then we get a clash and no answer set. And that is how we defined conflict or conflicting rules. So two rules are prime or conflicting if they have complementary head literals, and both bodies can hold simultaneously. And as I said before, there are many theoretical approaches available. We took one, in this case, the approach by Ita and his group, which is called update by causal rejection, where he takes an update sequence of n programs, and every program in a sequence updates all the programs before it. And he takes all the rules, puts it in one program, which he calls the update program, and modifies the rules. And one main aspect is the addition of a reject atom, which says that rule R is rejected. And yeah, as I said, with the update sequence, we have many programs which updates all the others before. And in the case of update by causal rejection, if two rules between two programs are conflicting, he rejects the rule of the older program, and so that only the rule of the newer program holds, and so that we don't get a conflict. So older knowledge which is in conflict with newer knowledge gets ignored. And what we did is we used this approach to detect all conflicts in an update. So first of all, we limited the update sequence to 2 programs because that's enough for a proof of concept. So if we want to update a program P1 with a program P2, we first detect the conflicts. And for that, we use the update by causal rejection, but in a modified way, where I add another literal reject cause, RR prime, which tells me that if it is in an answer set of my modified update program, it tells me that rule R is rejected because of rule R prime. So all the reject cause literals in an answer set can tell me where the conflicts are. So they represent a conflict. And it's important to state that our modified update program is not the final updated program. It's only an intermediate step to detect all the conflicts. So in detail, our modified update program takes all the constraints of P1 and P2, and for all rules of P1, it adds not reject to the body of the rule. So it gets rejected if it's in conflict with a newer rule. And for all rules of P2, we take the rule as they are, but we duplicate each rule and replace the head literal with active R prime. And that is kind of a flag that the body of R prime is true, which we will need. And then for every rule pair we can find between rules of P1 and P2, where we have complementary head literals, we add 2 more rules. The first one is the first one says that if the body of the first rule holds and the body of the second one of the second rule holds, then we have to flag it again by reject cause. And to prevent the older rule from firing, we also need the second rule, which gives us the reject atoms in our answer set. And another modification is that each head literal is indexed by the program which it is from. So all the head literals from P1 are indexed with 1 and from P2 with 2. And with the inertia rules here, we get to the original literal at the end. But let's look at our example from before. So we already realized that R3 and R5 were conflicting. And for these two rules, our modified update program would have the following rules. So R3 would be taken over as it is, but with not reject R3 at the end. And for R5, we take the whole rule and we add another rule with active R5 in the head. And then we say, when we have a rule which says that rule 3 holds, which is the original body here, and rule 5 holds, so active R5, then we have reject cause R3, R5. And of course, the reject atom here, which we can get from reject cause. And that we would do for the whole program. So the whole program would be modified like this. And in an answer set for this program, we would get all the facts. And then we get low success 2 bar, which stems from rule 5. And because of the inertia rules, we get low success bar. And then because R5 holds, we get active R5 too. And then the most interesting part is we get reject cause R3, R5. And that's our conflict. And then we need reject R3 so that low success won't be in our answer set, so that we get an actual answer set. Okay, so we have all the conflicts, and then we developed a method on how to assist the medical expert to find a resolution or a solution for the conflict. And we have a quite simple method where we look at the body literals of two conflicting rules and take the difference of the body literals. In this case, it's immunotherapy and not without crisis. And we say, okay, if we take at least one of those literals and put it in the other rule of the conflict pair, but default negate it, then we have that the two rules can't be conflicting anymore. So for our example, we would have 3 suggestions for rule 3. So either we add not immunotherapy to it, or just without crisis, because the default negation of not without crisis is just without crisis, or we take both of them. And so we can see that R5 and, for example, R3 prime are not conflicting anymore, because the bodies can't hold simultaneously. So yeah, that's our approach. As we saw with the modified update program, we can detect all the conflicts through, and they are represented by the reject cause literals in an answer set. And with the suggestions, the medical expert can resolve each conflict and decide if he wants to resolve it by choosing a suggestion, or the medical expert can define a new rule by himself. And then we get 2 modified programs, P1 head and P2 head, with all the modified rules. And because they have no conflicting rules, we can just merge them together and we can unite the two programs, and we have an updated program. So the update at the end is done by simply putting all the modified rules and original rules which weren't conflicting together in one program. So to conclude, we presented a method to interactively update answer set programs with the help of an expert by detecting conflicts and resolving them. And to assist the expert, we generate suggestions. And the expert involvement ensures the correctness of the update, and the suggestion of resolution resolutions eases the conflict resolution process. And for future work, of course, the implementation is important. The implementation of the whole method, and also we have to look at other strategies to detect conflicts, and especially we have to extend the strategies used for the generation of suggestions, because here we only use default negation, but it is possible to do it with classical negation and with a combination of both, and I think other strategies are possible too. And another aspect which we are currently working on is detecting conflicts independent of their effects, because as we saw in our example, if we didn't have a treat as effect in our program, we never would have found R3 and R5 as conflicting rules. And especially for real life applications, we have to be effect independent when we update programs. So that's one issue too. Yeah, that concludes my presentation. So thank you for your attention.